Have you ever found yourself just staring at a screen full of code? And even though you know it works, your brain just feels sluggish.
Yeah,
Like
definitely.
you're wrestling with some kind of invisible force, just trying to decode what should be simple.
Mm-hmm. That mental weight, right? That
Yeah,
unseen friction.
exactly. It's not just you, it's actually a growing challenge in software development. And, well, the industry has started calling it out by name cognitive load.
Yeah,
Welcome to the deep dive. Today, we're really going to try and unmask this invisible burden.
sounds good.
It feels like this term cognitive load has suddenly, I don't know, exploded from like educational psychology into our daily developer chats.
Uh-huh. Especially places like Hacker News, you see it all the time now.
Right. It's no longer some obscure academic concept. So what's driving this sudden widespread recognition? Why now?
Well, I think it's a direct response to what a lot of people are calling a crisis of complexity. Our mission in this deep dive, really, is to understand why human attention seems to have become the main bottleneck, in software productivity quality.
Right, the human limit.
Exactly. We're going to try and bridge that crucial gap between, let's say, a developer's gut feeling of being overwhelmed
Yeah, that ugh moment.
and the rigorous scientific framework of cognitive load theory. We're pulling together industry discussions, academic principles, and key works like John Ousterhout's philosophy of software design.
Okay, so we've always tracked things like performance, feature velocity, uptime. Those are still crucial, obviously.
Of course.
But you're suggesting we need a new kind of metric, one focused on the human element. Why isn't fast or functional enough anymore? What makes this cognitive cost so critical?
Well, high cognitive load doesn't just mean a developer gets frustrated. It actually directly translates to slower development cycles, more bugs, and yeah, increased burnout.
Real consequences.
It's a real economic and frankly human problem. If we ignore it, we risk stifling innovation, losing talent. The shift is towards realizing that the human mind, not just the machine, is our most constrained resource.
Okay, so the big question then is how do we even begin to recognize this invisible burden when it's so, well, inherent to thinking?
That's the challenge, isn't it?
What's truly fascinating, I think, is how developers are instinctively grappling with this, often before they even put the formal name cognitive load on it.
Uh-huh. You see the patterns in the advice.
Yeah, the core idea bubbling up is that minimizing cognitive load should be like a main goal in software design if you want code that's maintainable and high quality.
Right, for the long haul.
So, okay, if we're trying to lighten that mental burden,
Yeah.
what are some of the first practical steps people are taking? I've seen loads of talk about simplifying conditionals, for example.
It's a great one.
What does that actually look like, on the ground? And why does it help so much?
You're hitting on a key point there about reducing what the theory calls extraneous load.
Extraneous load.
So you take a sprawling if statement, like if user dot is valid and does user dot is blind and it has permission. It's a bit of a mouthful.
Yeah, you have to track each part.
Exactly. And you break it down. You create a descriptive Boolean variable, can perform action, user dot is valid, and then use that and is blocked and has permission, and then just if can perform action.
Ah, okay. So you give the complex condition a name.
Precisely. You immediately reduce the number of separate logical things your brain has to juggle
Hmm.
in its very limited working memory. It's about presenting the info in a way that needs less mental gymnastics.
So it's not just shorter code, it's easier to parse mentally,
Yeah.
less work.
Exactly. And we see this elsewhere too. Take early returns, sometimes called guard clauses.
Right, checking the error conditions first.
Yeah. You handle the edge cases right at the top of a function.
Yeah.
That isolates the main logics, the happy path.
Hmm.
And that dramatically reduces the mental effort you need to trace deeply nested structures.
Hmm.
Your brain doesn't have to keep track of multiple branching conditions as it dives deeper and deeper.
That makes so much sense. I mean, I think we've all gotten lost in a nested if-else jungle more times than we care to admit.
Oh, absolutely.
You mentioned John Ousterhout before. He talks about deep modules versus shallow modules. How does that fit in?
Ousterhout's concept of deep modules is really powerful here. These are modules with simple, narrow interfaces that hide significant internal complexity.
Okay, simple on the outside, complex on the inside.
Right. Contrast that with shallow modules, where the interface is almost as complex as the implementation itself. It doesn't really hide much.
So not much benefit.
Exactly. A deep module helps you encapsulate complexity. You only need to understand the simple interface to use it, not all its intricate internal workings. This directly cuts down the extraneous load for anyone using that module.
Gotcha. And what about things like how we represent data? You mentioned self-describing values.
Absolutely. I mean, why use an opaque HTTP status code like 400 bad request when you can return something like error, insufficient funds?
Right. The second one tells you exactly what happened.
Yeah. It tells you exactly what's wrong without forcing you to mentally map that generic code to a specific business role, that mental mapping. That's pure extraneous load.
Okay.
And then there's the whole tricky area of DRY. Don't repeat yourself. The advice here seems more nuanced now. It's not never duplicate, but maybe avoid premature or flawed abstractions.
Right, because a bad abstraction can be worse than duplication.
I think we've all been there, right?
Yeah.
Trying to abstract something just in case and ending up with this spaghetti monster of indirection. It's a really tricky balance.
Yeah.
When does simple duplication actually create less cognitive burden than a complex abstraction?
That's a great point. Sometimes the clever solution is just the least comprehensible one for everyone else.
Mm-hmm.
And avoiding anti-patterns fits right in here too, like deep inheritance chains or too much framework magic that forces you to build this huge mental model just to do something simple.
Yeah, all that hidden stuff you have to keep in your head.
So what you're really highlighting is that these practical tips, they're mostly focused on reducing that extraneous load, the mental effort that doesn't really help you understand the core problem.
Exactly.
So most code complexity isn't actually inherent to the problem. It's often self-inflicted through just, well, poor information design.
Precisely. We're seeing developers instinctively moving towards better information design within their code, making it easier for the next person or their future self to understand.
This leads us to another really compelling aspect. The community isn't just, nodding along. They're adding layers of nuance and some healthy debate.
Oh, yeah, definitely.
For example, this whole idea of the subjectivity of simplicity. What's simple for an expert, someone who lives and breathes terse functional code, might be overwhelmingly complex for a novice used to, say, imperative loops.
Right. Context matters hugely.
And this reflects something called the expertise reversal effect. Apparently, techniques that help novices can actually hinder experts, and vice versa. It really tells us that simplicity depends a lot on your audience's existing mental models, their schemas.
That's a crucial point. There's no one-size-fits-all simple.
Then there's the classic dogma versus pragmatism debate. You see this constantly, like early returns versus insisting on a single exit point for functions.
Citing things like the NASA C style guide.
Exactly. Or the correct way to apply DRY. This isn't just about syntax. It highlights that tension between, say, team consistency and optimizing a specific piece of code for local clarity.
Right, the local optimum versus the global standard.
And the limits of abstraction. Remember the custom JSON errors versus standard HTTP codes. A custom payload might reduce cognitive load for the application developer.
But it could increase it for an operations team or maybe client developers who now have to learn this non-standard thing.
Yeah, it just shifts the burden. It's always a trade-off, isn't it?
Always. And crucially, this conversation also brought up the human factor. You remember Microsoft's developer personas? Mort, the pragmatic coder, Elvis, the innovator chasing cool tech, Einstein, the theoretical perfectionist?
Right, and the proposed ideal, Amanda, who focused on team cohesion and simplicity.
Yeah. And the discussion highlighted how, Elvis's cleverness or Einstein's theoretical purity, while maybe impressive on their own, can actually generate complexity, generate extraneous load for everyone else.
Well, Amanda prioritizes keeping the cognitive load low for the whole team.
Exactly. It's a different focus.
And looking ahead, you can't ignore AI in this discussion. The specter of AI is huge. There's anxiety, right? That AI could just churn out hyper-complex, unreadable black box code. Functional maybe, but impossible for humans to maintain.
That's the fear.
But then there's the hope that AI will automate away all the tedious, low-level stuff.
Yeah, the boilerplate.
Freeing up human developers to focus on the big picture, the high-level problem-solving and architecture. It feels like managing cognitive load is going to be absolutely central to how that human-AI collaboration evolves.
I completely agree. The ultimate success of AI in software development will probably hinge on its ability to manage the cognitive load of its human partners. AI tools have to be designed with this theory in mind to be effective teammates.
Okay, so we've explored the industry's sort of intuitive grasp of this problem, the practical things people are trying. But to move beyond just intuition, to get a really rigorous understanding, we need to talk about the science behind it.
Right, John Sweller's cognitive load theory. It originated in educational psychology, but it's incredibly relevant here.
So it gives us a formal framework for what's actually happening in our brains when we're coding or reading code.
Exactly. At its foundation, CLT describes our cognitive architecture. We basically have two key memory structures involved in learning and problem solving. First, there's working memory. That's our conscious processing space. Think of it like your mental RAM, but it's severely limited. It can only hold maybe about 4 chunks of information at a time.
Only 4. Wow.
Yeah, the estimates vary a bit, but it's small. And that information decays really fast within seconds if you're not actively rehearsing it, keeping it alive. It's the critical bottleneck for all active thinking.
Okay, so if I'm trying to hold too many variables, function calls, logical conditions in my head simultaneously, my working memory just hits a wall quickly.
Exactly, it gets overloaded. Then there's long-term memory. Now, this is functionally limitless. It stores information in these organized knowledge structures called schemas.
Schemas, like mental framework.
Precisely. Think of schemas as blueprints or patterns. An experienced programmer, for instance, has a well-developed schema for a for loop. They understand its syntax, its purpose, common uses, potential pitfalls, all as a single coherent concept.
So they don't have to think about each little piece of the loop every time.
Right. It allows them to treat for loop as one chunk in working memory, effectively bypassing its limits for that concept. Learning, therefore, is largely about building and automating these schemas, storing them in long-term memory.
That makes so much sense. It explains why an expert can glance at complex code and sort of get it almost instantly, while a novice really struggles line by line.
Yeah, their schema library is just so much richer and more automated.
Okay, so working memory limited, long-term memory schemas vast. What are the types of load?
Right. CLT identifies 3 types of cognitive load, and crucially, they all draw from that single finite pool of working memory capacity.
Okay, 3 types, 1 pool.
First, intrinsic load. This is the inherent, unavoidable difficulty of the subject matter itself.
The core complexity.
Yes. Understanding something like recursion or multi-threading has a high intrinsic load because it involves many interacting elements you have to process at the same time. You can manage it by breaking problems down into smaller steps, but you can't eliminate it without changing the fundamental problem.
Got it. So intrinsic load is the problem itself. What's next?
Second, extraneous load. This is the bad load. It's mental effort that doesn't contribute to actually learning or understanding the core problem.
Wasted effort.
Essentially, yes. It's generated by how information is presented. Things like poorly named variables, inconsistent code formatting, fragmented documentation scattered everywhere, or having to constantly flip between multiple files just to understand one function.
Okay, so stuff that makes the code harder to read or follow than it needs to be.
Exactly. The primary goal here is always to minimize extraneous load. Get rid of the unnecessary friction.
Right. And the third type?
The third is germane load. This is the good load. It's the mental effort. You actually want the effort devoted to deep processing, connecting new information to your existing schemas, and constructing new schemas in long-term memory.
So this is the actual learning part, the aha moment.
Precisely. It's where understanding happens. The goal is to optimize this, but, and this is critical, you can only really engage in germane load effectively if you first minimize the extraneous load. You need to free up the mental resources.
Because all 3 loads draw from that same limited working memory pool.
Exactly. This creates a zero-sum dynamic. An increase in extraneous load caused by, say, confusing code directly cannibalizes the cognitive capacity you have available to grapple with the problem's intrinsic difficulty, intrinsic load, and to engage in that deep understanding, germane load.
Wow, okay.
This explains precisely why ugly but functional code is so detrimental. It's not just an aesthetic issue, it's a cognitive drain. It actively prevents developers from understanding the core problem deeply and devising better solutions. It provides a solid scientific justification for philosophies like clean code.
That's a really powerful argument for focusing on clarity and simplicity. It's not just nice to have, it directly impacts our ability to think.
Absolutely. It frees up the bandwidth needed for the real work.
But I can imagine someone pushing back, right? In the real world, sometimes good enough or just ship it wins out. Are there situations where trying too hard to reduce cognitive load might become its own problem? Like over-engineering?
That's an excellent point, and it's about balance. While minimizing extraneous load is almost always good, you can overdo it. For example, creating layers upon layers of abstraction for future needs that never materialize.
Right, the YAG&I principle, you ain't gonna need it.
Exactly. That kind of premature abstraction can create new extraneous load if the abstraction itself isn't clear, or if it forces developers to understand this complex structure that doesn't actually provide much benefit yet.
Or it might simplify things for one person, but complicate it for someone else.
Right, like the custom error codes example. Reducing load for the API producer might increase it for the consumer. This framework doesn't give you magic answers, but it helps you diagnose those trade-offs more clearly. Are we reducing extraneous load overall, or just shifting it?
That's a great segue. Now that we have this powerful framework, this scientific lens, let's put on our goggles and look back at that developer discourse we talked about earlier. Let's reinterpret it with more precision.
Yeah, it's like having a Rosetta Stone, right? Translating developer complaints into a formal diagnosis based on CLT.
Okay, let's try it. That clever or magic code that makes you scratch your head. Using our new framework, we can see that as just high extraneous load. It uses non-standard patterns, requires extra mental decoding.
Exactly. And a leaky abstraction where implementation details aren't fully hidden like they should be.
That increases intrinsic load, right? Because you suddenly have more interacting parts to think about than the abstraction promised.
Precisely. Or consider the trend of having maybe too many shallow microservices. While it might reduce the intrinsic load of understanding any single service,
It can massively increase the extraneous load from all the complexity of how they interact, the network calls, the deployment coordination.
yeah, the system level complexity goes way up.
Okay, but on the flip side, a really good abstraction or API.
That fosters germane load. It helps you build a new, powerful schema. It packages complex ideas into an easily digestible chunk, reducing future cognitive burden every time you use it.
And what about constantly having to cross-reference files or look up documentation just to understand one piece of code?
Classic high extraneous load, often due to something called the split attention effect. Your working memory gets totally taxed trying to mentally integrate information that's physically separate.
So this translation, this Rosetta Stone, it lets engineering leaders move beyond just saying this code is a mess
Uh-huh.
to actually treating root causes. Like, okay, we need to reduce extraneous load here by improving our naming conventions, or we need to simplify these module interfaces. It sounds like a game changer for how we discuss code quality.
It absolutely is. It gives you a much more precise vocabulary. And this naturally raises the question, does this thinking apply beyond just lines of code? Does it scale up to entire system architectures?
It feels like it has to, right? A system is just a big collection of code and interacting parts.
Precisely. Cognitive load principles extend directly into system architecture and design philosophy. You can actually read John Ousterhout's Philosophy of Software Design as basically a comprehensive guide to minimizing extraneous cognitive load at the system level.
Ah, interesting lens.
His concept of deep modules, for instance. That means a module contains high intrinsic load internally, handling complex stuff, but it presents a low extraneous load interface externally, simple to use.
Okay, that's a powerful way to manage system-wide complexity. Hide the hard parts.
Exactly. And Ousterhout's maxim to pull complexity downwards.
Yeah.
That's a direct instruction for module authors. Accept a higher cognitive burden yourself during implementation to spare the many, many users of that module from facing the same burden later.
Wow.
It's a strategic investment in reducing the organization's overall cognitive load. He also identifies dependencies and obscurity as primary causes of complexity, and those map directly onto intrinsic and extraneous load generators.
So it's about making a conscious choice to shoulder more complexity as the creator so that countless other developers downstream don't have to. That feels like a fundamentally almost altruistic design philosophy.
It kind of is, in a way. And this architectural perspective also leads naturally to the concept of cognitive debt.
Okay, like technical debt, but for brain power.
Exactly. Just like technical debt comes from taking shortcuts in implementation, tactical programming that cuts corners on clarity, on good abstractions, on managing dependencies that creates a cognitive debt.
And the interest payments.
The interest payments are paid by every single future developer who has to expend extra mental energy, extra working memory capacity, just to understand and work with that now more complex system.
Oof, that adds up fast.
It really does. Framing it this way provides a compelling business case for investing in strategic design up front. It's not just about elegance, it's a direct investment in future development velocity and reducing ongoing costs.
That's a brilliant way to put it, cognitive debt, because it really is a burden passed down through time. But, it's not just the code or the architecture. It feels profoundly human, too.
Absolutely.
Remember those developer personas we talked about? Elvis, the clever innovator, and Einstein, the theoretical perfectionist. They can actually be primary generators of extraneous load.
Because their pursuit of novelty or theoretical elegance might result in code that's just really hard for the rest of the team to grasp.
Right. And Mort, the pragmatist, just trying to get it done, might take shortcuts that accumulate that cognitive debt over time.
Mm-hmm.
But Amanda, the cognitively aware engineer, she optimizes for low team-wide cognitive load. She prioritizes consistency, clarity.
Because she understands that the team's shared mental model, their shared understanding, is ultimately more valuable for productivity than any individual's momentary cleverness.
That really underscores that cognitive load isn't just an individual thing. It's a team-level phenomenon.
Absolutely. A team's overall effectiveness is deeply tied to their shared cognitive load, their consistency, their shared mental models. And this has a massive impact on culture.
How so?
Well, think about it. High cognitive load environments where code is confusing, dependencies are tangled, changing anything feels risky that leads to stress, anxiety, a fear of making changes. It can easily foster a culture of blame when things go wrong.
Yeah, nobody wants to touch the scary module.
Exactly. Conversely, a low-load environment where things are generally predictable and comprehensible, that fosters psychological safety. People feel confident making changes, experimenting, collaborating on problems. Reducing extraneous load isn't just a technical initiative. It's a direct investment in building a healthy, resilient, productive engineering culture.
That's huge. Okay, looking ahead again. The next frontier for all this is undoubtedly the age of AI-assisted development.
Definitely.
There's that optimistic vision, right? AI is this amazing extraneous load reducer, automating boilerplate, generating documentation, maybe even explaining complex code snippets to you. Sounds incredible.
It does sound amazing.
Yeah.
But there's also the pessimistic view.
Right. The fear that AI could just generate functional but totally unreadable, incoherent black box code, stuff that drastically increases both extraneous load, because how do you even read it, and maybe even intrinsic load for the humans trying to maintain or debug it.
Yeah, the complexity could become overwhelming. The new germane load, the valuable cognitive work for developers, might shift significantly. It might become more about prompt engineering, critically reviewing AI output, verifying correctness, integrating it safely.
So the skill becomes less about writing the code line by line and more about guiding and validating the AI, assessing the cognitive load impact of what it produces.
That seems very likely. As it was said before, the success of AI in software development might really hinge on its ability to manage the cognitive load of its human collaborators. AI tools need to be designed with CLT in mind to be truly effective partners. They need to produce not just code, but comprehensible code that genuinely reduces the human burden.
Okay, this has been fascinating, digging into the theory and the discussions. So for you, listening right now, whether you're a developer on the front lines, a team lead, maybe someone influencing organizational strategy, what can you actually do with all this? How do we translate this theory into tangible action?
That's the key question. Let's make it practical.
Okay, so for the individual developer, maybe it starts with just self-regulation. Things like the Pomodoro technique, those focused work sprints.
Helps manage working memory.
Right, plus task batching, maybe more mindful coding practices, just being aware of your own cognitive limits.
And adopting coding practices explicitly aimed at reducing load for others. Writing self-documenting code, using really clear names, maybe preferring composition over deep inheritance, decomposing complex problems into small, understandable units.
So you're lowering the extraneous load for your teammates and honestly for your future self when you come back to that code 6 months later.
Exactly. Yeah. And crucially, continuous learning, actively working to build and automate schemas in your domain, your language, your tools. That's how you convert high intrinsic load into low-cost automated knowledge in your long-term memory, freeing up working memory for the really novel problems.
Okay, that's the individual level.
Right.
What about team leads and architects?
Well, they need to lead the charge. Champion consistency. Establish and enforce clear coding standards, naming conventions, architectural patterns. That reduces team-wide extraneous load because everyone knows what to expect.
Makes sense. Less surprise, less decoding needed.
Make strategic code review a priority. Don't just check for correctness. Explicitly evaluate pull requests for clarity, simplicity, and cognitive load. Ask that question, is this the simplest, clearest way to present this solution to another human?
That's a great code review question.
And make architectural decisions with cognitive load as a primary factor. Actively favor deep modules, strong information hiding. Consciously analyze the cognitive load trade-offs, like when choosing between a monolith or microservices or introducing a new framework.
Okay, and scaling up even further, for the entire engineering organization, what's the play there?
It really comes down to culture and infrastructure. Foster a cognitively aware culture. Make cognitive load part of the shared vocabulary. Explicitly treat developer attention and focus as a precious, finite resource.
So it's okay to talk about code being hard to understand, and that's seen as a valid problem to fix.
Absolutely. And invest in developer platforms and golden paths. Tools and infrastructure that abstract away incidental complexity, things like deployment, monitoring, standard libraries. This dramatically reduces extraneous load on product developers so they can focus on business problems.
Right, let them focus on the intrinsic load of the features, not the plumbing.
Exactly, and align incentives. Reward engineers who demonstrably reduce complexity, improve clarity, and promote team effectiveness. Reward the Amanda persona, not just the Elvis who builds something flashy but complex.
Interesting point about incentives.
And finally, design onboarding for load management. Structure the process using CLT principles. Start with worked examples, provide scaffolding, and then gradually increase the complexity and reduce the support, a technique called fading guidance. Don't just throw new hires into the deep end of a complex system.
Wow, okay. That's a comprehensive toolkit from individual habits right up to organizational strategy.
You can think of this toolkit as your personal Rosetta Stone for putting CLT into practice. Looking at the bigger picture, it's really about systematically chipping away at unnecessary complexity at every single level. It's about ensuring our limited cognitive resources are spent solving meaningful problems, not just deciphering needlessly difficult code or navigating overly complex systems.
So cognitive load. It really is that invisible friction, isn't it? That tax on developer attention. And all the industry discussions we're seeing, they're a clear signal that this tax has just become far too high.
I think that's right. The ultimate goal here needs to be a fundamental shift in mindset. Moving beyond creating software that merely functions to building software that is truly comprehensible. It's about fostering a genuinely cognitively aware engineering culture, one that recognizes developer cognition as the most precious and most constrained resource we actually have.
So maybe a final thought for you listening. Consider how actively reducing cognitive load in your own work on your team isn't just about making things, more efficient or less frustrating.
Yeah.
It's really about freeing up your and your team's most valuable asset, that finite mental bandwidth, so you can engage in true innovation, in curiosity, in the kind of creative problem solving that actually leads to breakthroughs rather than just getting by.